So, good evening and welcome to my stream. Yeah, sound seems alright. Okay. Then today, Advent of Code 2025, day 11. This time a little bit later than usual. It's 8 o'clock here. Normally I do it at 7:30 in the morning. Now we have 8 o'clock in the evening. Today I just couldn't manage it in the morning. Today I hope for the last I will be able to do it in the morning again, just for the finish. Yeah, so let's head into the task. Day 11, reactor. You hear some loud beeping coming from a hatch in the floor of the factory, so you decide to check it out. Inside you find several large electrical conduits and a ladder. Climbing down the ladder, you discover the source of the beeping, a large toroidal reactor which powers the factory above. Some elves here are hurriedly running between the reactor and a nearby server rack, apparently trying to fix something. One of the elves notices you and rushes over. It's a good thing you're here. We just installed a new server rack, but we aren't having any luck getting the reactor to communicate with it. You glance around the room and see a tangle of cables and devices running from the server rack to the reactor. She rushes off, returning a moment later with a list of the devices and their outputs, your puzzle input. So, this here. And each line gives the name of a device, followed by a list of the device to which its outputs are attached. So BB, DD, EEE means that device BBB has two outputs, one leading to the device DDD and the other leading to device EEE. The elves are pretty sure that the issue isn't due to any specific device, but rather that the issue is triggered by data following some specific path through the device. Data only ever flows from a device through its outputs, it can't flow backwards. After dividing up the work, the elves would like you to focus on the devices starting with the one next to you. An elf hastily attaches a label which just says you, and ending with the main output to the reactor, which is the device with the label out. So this is our starting point, and these are our endpoints. To help the elves figure out which path is causing the issue, they need you to find every path from you to out. In this example, these are all of the paths from you to out. Data could take the connecting from U to BBB, then from BBB to DDD, then from DDD to GGG, then from GGG to out. So here we can see it here. It's it's U, then BBB, then from BBB to DDE would be one path. That would go to GGG, and that would go directly to out. Or we could go over C and over C to D again, and that would again lead to G, which leads to out. And so we have to follow all the paths here. That's what it says here. And in total, there are 5 different paths leading from U to out. How many different paths lead from U to out? So that is our task. And I've already thought about the task because, I read it in the morning and then couldn't, really implement it. But we have a list. Let's try to copy this over to our drawing board. Yeah, I mean, it's all right. Oh, the scrolling is inverted. That is not confusing at all. And I can zoom in, but I can't zoom out. That is perfect. Let's reload this page. Yeah, that's better. Okay, no tool to zoom. Apparently, I will try to zoom one more time. Okay. Yeah, that's better. So what we're going to do is we are going to simply create, give me a second. Let's choose a color fill with, let's say, red. Okay, so what we're simply... Oh, nope. I don't want to fill, actually. Can we say no fill again? I think we cannot. Okay, this... No, it seems like... Yep. Okay. Let's reload this. And let's go for the pen again. Why can't I turn this off again? Can't I say no fill again? Ah, okay. Now I have the no fill. Now we can say that we want a red outline, and that should be... Yeah, this seems all right. Okay. Then let's undo. Can't undo further. Okay. So we're going to use a hash map. And that hash map is going to contain on the left side all our keys. So these are our keys. And then on the right side, each key is associated with a list of values. And we first construct that so that we essentially have a list which is exactly our input here. So we have a map which has lists on the right side, and that will be our input. And then we simply go from the key u as the list input. So this is our first list input. And then we're going to say, okay, add these two to the next list. And then we have BB and we have CC. And actually what we have to do is we have to use a vector of vectors. And those can then be answers. That will be okay. And then we can build from U. We duplicate this for each, so that in our vector of vectors, we then have the vector that contains U and BB and the vector that contains U and CC. And from there, we look up BB once and CC once. And then for BB, we will get the U, BB, DD, and U, BB, EE, and so forth. And we will do the same with C. And this way, we always duplicate our list entries from there. And then we simply follow the path to the end. And then we have our output. I think that should be efficient enough in Rust. If our vector of vectors is exploding, we actually don't have to keep track of all the different things we are following there. We could also only track the last ones. But yeah, I think it will be all right to take the same thing. To keep track of everything. Okay. Then, yeah, after this wonderful drawing I made, let's go back to our input here. And I already copied everything over here, so we can simply switch over to Visual Studio Code. And yeah, let me show you what I have here. I have the main, which has all the different days, and today we are at day 11. And here I already copied the input into the resources. And then we have solve A and solve B. Solve B is currently here. And it's just marked with some stuff, so the compiler isn't unhappy with us. And then we have solve A here. And that is where we will start now. Here we already have the test case, which was on the task for today. And the result was 5, so we will assert that the result of solve A will be 5. So from here, let's, okay. Yeah, from here, let's first split our input into the map we want to create here. So let's say input split on \n, and then we need to map our lines. So then let's say line split on colon. Let's make this a multi-line function. So, okay. And then let's say, yeah, parts. I'm not creative right now. And then I think we should collect this into a vector. So vec of wildcard type. So then we have our parts. And then our key would be parts at 0. And then we need our values, which will be a list of parts at 1. And then we have to split them on space. And I think we should trim this before. So we should remove the white space because we split on the colon, then we have a space in the beginning, and if we split on this, we get an empty string. But so an empty string as the first element here. But if we trim it, the space is removed, and then we have BB and space CC. So this will simply result in BB and CC as the lists here, and that is what we actually want. So then, yeah, we have our keys, we have our values, but we actually don't want to map this. I think we simply want to fold this. So folding this into a hash map would be the most sensible. Then we have our accumulator and our line. We can keep changing our line here. And then in the end, we have to return our accumulator. And then we say accumulator at key is equal to values. And the type inference should... we have to say mute, of course, otherwise we cannot mutate it. But the type inference is not sure what we want here in the end, so we have to tell it that we want an answer mapped to a vector of answers. And now the compiler should be happy, but it isn't because I used the generics on the function, but we don't need the generics on the function, we need it on the type. So this should work. Okay, yeah, this needs to be collected. And then remove this mute. Variable does not need to be mutable. And this says we have to use insert. Okay. Then we say insert key and values. It is essentially the same, so it doesn't really matter here. Okay. And now we already have our table, which is now a hash map of answers onto vectors of answers. So this is essentially, these keys are mapped onto lists of this. So that is exactly what we want. And now we start with our node list, or how should we name it? Let's name it node list for now. This would be a vec. Let's use the vec macro for construction. And then what we want to start with is u. And then we say while node list is empty. Is not empty? No. So is empty not. So while this is the case, we do the following. We iter over the node list. So for node in node list. Yep. It's not happy with us here. Borrow of moved value node list. Yeah, it's moved because we are actually taking ownership when we just use it like this. But if we say iter, we are not taking ownership. And we can now dereference the string here because the answer is still just reference. And then we have a node. For example, in the beginning, it will be u. And then we need to construct the next node list. We can also simply construct a vector here. But we have to say that this is mutable, and the compiler isn't happy with us because it doesn't know the type yet, but it will know soon. So, and now for our node, we simply make lookup for next in table at our current node. Don't know why I made this semicolon. So, and this is fine. Okay, nice. And then what we do now is this will be a vector of vectors. So we take the original vector. Wait, something is wrong here. Yeah, it's wrong because this should actually be a vector of vectors here. And this will be then in the end 2. What we actually can do is node list is equal to next node list because that is what we want to do in the end. We then have to make this mutable, then it's all right. Okay, and then, yeah, now this isn't happy because we try to index with a vector into something that has a string as index. So we have to say last here and unwrap because last could be is an option. We need to unwrap this. And now this is, again, we have to say iter because implicitly into iter is called. And this is cannot move out of shared reference. I think we can say into iter here actually. And then we can't dereference this, but this is all right now. Okay. So why can we say into iter? Because this node list, the actual value behind it, will be dropped at the end of the while loop. Because we say here node list is equal to next node list, the original node list will be dropped here. That is why we can actually consume the value here into the for loop. So that because we drop it down here, we only iterate once over it. So we can actually take it as the value that it is. And then we don't have a problem with shared references because then the reference is only here. And after that is done. So then here we have our next. And there we simply say clone this list because we have to take that multiple times. Let's call it nodes. I know the naming today is really crap. And then we say nodes push our next. We have to make this mutable here. Now is simply appending. So if we had u, for example, we have here the vector with u, the vector of vectors with u. And then we have u and bb and u and cc after we are done with this here. So, and we push the next node, and now we have to push the node into the next node list. Exactly. So what's the problem here? Borrow of moved value node. Yeah, of course, because we actually named the one thing nodes and the other we named node. That is, let's name this node clone. Describes it better. Okay, so and now we have actually constructed here already all the paths when we are done. So we start with u, While this isn't empty. Yeah, okay, that is something we have to do. Let me quickly think. So if something ends, so if we have an out at the end, if the last element here. Yeah, okay, so we have to say filter, and we have to take lists where the last element is not out. And this is a problem because we have to dereference this once, probably, yes. And it's empty. We have to say for that this holds for any element. So for any element, it holds that the last element of the list is not out. Okay. This is our while loop. Yeah, and here we also... So we want to keep track of this. Then let's actually say this is node list, filter, and now we want all lists where the last element is equal to out. That feels like we're doing some work twice. Let's look for optimizations later. Then we collect this into a vector. We have to say that we want this to be next node list. The type annotations needed. Yeah. Vec of answer. Right. One more. Yeah, and now the problem becomes that we actually have to say that we need to clone those lists. No, I have a better idea. We can actually use... Can we? Yeah, I think there is a function in the Rust standard library that splits on an argument. Partition. Partition point doesn't sound right. No, I think it's also in the iter crate on the iter type. Was it partition? Partition. Yes, perfectly. So consumes an iterator creating two collections from it. The predicate passed to partition can return true or false, and partition returns a pair where we have, yeah, that's exactly what we want. So we actually want to find the ones where it's not out and the ones where it is out. And we can simply do that here by saying last, yeah, L last unwrap is equal to out, and type annotation needed. Okay. So let's actually remove this. So next node list and nodes to iter will be the two things we want capture here. So type annotations needed, but why the compiler already knows the type here? Never mind then. Insert explicit types. Partition. The trade bound vec answer copy is not satisfied. The following. Extend add vector. So we have to say into iter, of course. Yeah, okay, now it is happy. And do we still need the type annotations? Let's see. Yeah, we still do. Okay, so we've petitioned into the next node list and the nodes to iter, and here we say nodes to iter can actually implicitly call into iter here. And then we have to say that our next node list is mutable. So, and then we simply make this while loop to a simple loop with first partition, and then we say if nodes to iter is empty, then we break out of our loop. This way we can first do the work here, we only do it once, and then we can break here. And yeah, everything else should be all right. And then in the end, we can simply take the node list. Oh, can we? We have to change something here. We have to say that the node list is equal to next node list here already. And then we should use the node list here. And then we simply count this. Let's see. Mismatch types is all right. We can simply say as num here. All right. Very nice. I wasn't sure, and as always, I'm quite impressed by the Rust compiler, because the Rust compiler actually notices that the node list is here we say into iter, which means we actually take the ownership of the node list and it cannot be used because it's moved here. But here the node list again gets the next node list, and this way it is before the break, not moved again. So the compiler knows at this point it will always be a valid list. And that is kind of insane that the compiler gets this. Even I had to think about that we would lose the node list. And the compiler just understands. Crazy. Okay, and the test is running, which is perfect. Then let's simply take a terminal here. And let's say cargo run. Yeah, nice. The only reason we took the terminal up here is so you could see this wonderful ASCII art. And then let's take the result here and hop over to the task again. And there we can put in the value again. And yeah, that's the right answer. You are 1 gold star closer to decorating the North Pole. So this was the first part of day 11. The rest of the stream we tried to solve part 2 of day 11. And yeah, it was really hard and I couldn't finish it on that day. But in hindsight, I think there is a pretty easy solution. And I will try to implement that on Tuesday the 16th. And yeah, if you watch this video before that, maybe you want to hop in. It will be 8 p.m. Yeah, European time. And yeah, see you then.